Okay, so we are now going to see this change of variables formula 1. There are also formula 2 and formula 3. Now before we see the statement of this lemma and before we start proving this, let us recall something from school calculus. Imagine this definite integral cos theta d theta. If you are very well versed with trigonometric identities, solving this integral is simply a matter of applying one such identities. You may recognize the fact that sin theta cos theta is 1/2 of sin 2 theta. That will let you instantly solve this problem. But say for some reason you do not remember that formula or you do not want to use it, still it can be done by substitution. You can either take cos theta equal to x or sin theta equal to x. Let me take say sin theta equal to x. What that essentially does is it introduces a new variable. The previous variable was theta, in its place so now we have a new variable x. What you did then after that, you differentiated both sides with respect to theta. That gave you dx d theta on the left side and cos theta on the right side. Now you see, whenever you were taught derivative, again and again it was told that this dx d theta, in spite of how it looks, is not a ratio. It is not dx divided by d theta, but rather you have to interpret it as the derivative of x with respect to theta. D theta was considered to be an operation that you applied on x to get whatever you get. However, in spite of that, very paradoxically, after this you wrote dx equal to cos theta d theta, as if this just simply refutes what was told to you about this derivative. On one hand, the teacher is telling you that this is not a ratio. On the other hand, the teacher seems to have multiplied both sides by d theta and obtained this final line. Okay, so there itself there is a little confusion, but the confusion actually goes away once you are told the real meanings of dx and d theta. I am not going into that part. So the thing here is this: after making this substitution, you have x here and you have dx here, and accordingly you also changed these limits according to this substitution, and you then got the integral. The question is, what permits you to consider a new variable and then you simplify the integral and calculate some value and declare that that value should be the answer? What is the justification for this? If someone challenges you that no, this actually is giving you something else, it's not giving you the answer that you are supposed to get, then how will you answer that challenge? That will be answered by these results, by the final result, actually the third one. So this is the first one. So let's now see its statement. So the starting point is just like before. You have two real numbers a and b such that a is less than b, so that this interval has some points, not just one point. And phi is defined on this interval, and phi is continuous and monotonically increasing, which makes phi as a function from this interval to this interval an onto function. The fact that phi is continuous and monotonically increasing ensures that the image set of phi is going to look like this. If you are wondering where this is coming from the last result on intermediate value property in the chapter on continuous functions, corollary 974. Okay, so that justifies this. So this is one thing. The other thing is that we also have a piecewise constant function f, whose domain equals the range of phi, so that we can consider this composition. The composition, of course, then will be a function from a comma b to r. The claim is that this composition will be piecewise constant as well, just like f. And the Riemann-Stieltjes integral of this composition with respect to phi on its domain equals the ordinary Riemann integral of f on the domain of f. So let's see the proof now. In the proof, we are first of all going to write what this right hand side integral is. Note that it's already given that f is piecewise constant. So it will be piecewise constant with respect to some partition of the domain of f, that means this interval. So this is how the proof starts. Let P be a partition of this interval WRT with respect to which f is PC, piecewise constant. We can also assume, without losing generality, that the partition P does not have the empty set as an element. Assume that the empty set does not belong to the partition. If originally it really belongs to the partition, you can just throw it out without affecting the fact that the resulting set again is a partition of this interval with respect to which f is still piecewise constant. For each element j, each subinterval j in this partition, let Cj be the constant value of f on j. Okay, because f is piecewise constant. Then this integral will be simply this sum. Okay, so we know what this right hand side is. It is this. We now have to prove that this left hand side is also equal to this. But let us also note that before we can think what this integral will be, we need to show that this composition itself is also piecewise constant. Note that in this entire thing there is no question of integrability. F is already piecewise constant, so it is Riemann integrable. And if we manage to show that this composition is piecewise constant as well, it will be Riemann-Stieltjes integrable with respect to phi. So we now need to guess that partition with respect to which f composition phi will be piecewise constant. So let us consider any j in P. We claim that the inverse image of j under phi is an interval. These are places in a proof where we can become a little confused unless we see the big picture. See the big picture means you need to see at once where these ingredients lie. This is what I precisely mean. So this, whatever I write here between dashed lines, that's not a part of the proof. What is our phi? Our phi is a function like this. Now what is j? J is a subinterval in the partition P, and P is a partition of what? P is a partition of this interval. So that means j is a subset of this interval. So you can now see that it's making sense. So phi inverse of j will be a subset of this interval. Okay. And we are claiming that this phi inverse of j itself is an interval. Alright. To show that it's an interval, since we are on the real line, so it's enough to show that this is a connected set. Because do you remember that when we started studying integration theory, at that time, at one stage we started studying connected sets, and it turned out that on the real line, connectedness of a set and it being an interval are equivalent. Any connected non-empty set is an interval, and any interval is a connected non-empty set, provided we are talking about non-empty intervals. Okay, so now we want to show that this phi inverse of j is connected. And what shall we need to do that? Let me extend this a little bit. So phi inverse of j is some set here. We will take any 2 points in phi inverse of j, say x and y, where x is less than y. If we manage to show that the entire line segment determined by x and y is inside phi inverse of j, then by definition of connectedness it will be connected. Because if something from the middle of x and y, in between x and y, fails to lie in phi inverse of j, then there is a break. So connectedness will be lost. Accordingly, let x and y we are going to keep this. Let x and y belong to this such that x is less than y. Because x and y both belong to this inverse image, so phi of x and phi of y will belong to j. Now recall that phi is monotonically increasing. Since phi is monotonically increasing, and that's why phi of x is less than or equal to phi of y. And j being an interval itself, because j is coming from P, it is also connected. Okay, so now if you see the picture, this is what j is, and inside j we have these 2 points, phi x and phi y. phi x is less than or equal to phi y. Why do we not write strictly less than phi y? Because it's given that phi is increasing, not necessarily strictly increasing, and we don't need that. Now j is connected, so the interval determined by these 2 points will be contained entirely within j. We have, I'm going to keep some space, you will understand why. This is entirely contained in j. However, this interval is equal to the phi image of x comma y. The question is why? This containment we understand, but why is this equal to phi of x comma y? That thing is coming from corollary 974. The fact that phi is monotonically increasing, again, you see in the statement also we said why the image set of phi looks like that, phi a comma phi b. Exactly that is why this also looks like this. So, but then if the phi image of this interval is contained in j, then the interval will be contained in phi inverse of j. So this is what we wanted to show, right? So phi inverse of j is connected and hence an interval. So we now again go back to that little diagram. Yeah, I should not have wiped it out, but anyway. So you have j here, which is coming from P and which is some subinterval there, and you have found that phi inverse of j is, of course, it's a subset of this, but it's also an interval. This gives us a hope, the hope that if we take the collection of all such phi inverse of j's, then its elements will be subintervals in this interval. Will that collection itself be a partition of this a comma b, with respect to which that composition, f composition phi, will be piecewise constant? If we can manage to show this, then one half of our claim will be true. But before we become too hopeful, let us also see what we are requiring of the collection of this phi inverse of j's. We want f composition phi to be piecewise constant with respect to the partition if it becomes a partition. Will it really be piecewise constant? For that, this composition needs to have a constant value on each such phi inverse of j. Let us see if that is true. Otherwise, there is no point going further. Next, for any x belonging to phi inverse of j, we want to show that when evaluated at x, this function becomes constant regardless of what x is. because x is there, so phi of x will belong to J. However, we already know something, since we know that f is piecewise constant with respect to the partition P, so f has a constant value on J, that's Cj. That means at any point of J, if we calculate f, we are going to get Cj, in particular at this point also. So f of phi of x will be equal to Cj, or f composition phi of x is equal to Cj. So yes, really at each phi inverse of J, this is constant. Now we just need to show that the collection of this phi inverse of J's is a legitimate partition. So we give it a name. Let's call it Q. Let Q be this collection. Now some things about Q we can say immediately. The first thing is that Q is finite. We need this for Q to be a partition. Since P is finite, so there are only finitely many J's, so they are going to give you finitely many inverse images, so Q is also finite. So is Q. Also, the elements of Q are bounded intervals in A, P. Yeah, now I think we have seen this enough, so I can just wipe it off. They are already, they are these sets which are already elements in this, so they are bounded sets because this itself is bounded, and just now we have proved that they are intervals as well. Okay. What else do we need for Q to be a partition? We need to next show that any element in this interval belongs to one such set coming from Q. That is one thing. And the other thing is that distinct phi inverse of J's are disjoint, mutually disjoint. So towards that direction, let X be any element in this. Then phi of X belongs to phi of this, which is just phi A, phi B. But P is a partition of this interval and this is an element in this interval. So this element will belong to some J in P. But if this is the case, then X will belong to phi inverse of J. Where of course phi inverse of J is an element in Q. So yes, any element in this interval belongs to some element of Q. Next comes the question of mutual disjointness. Next, consider distinct J1 and J2 in P. We have, so our aim is to show that this intersection is empty, because this will then be two distinct elements in Q and we want them to be disjoint. Having inverse images is a blessing, because inverse images behave well with union, intersection, everything. Okay, so you have this. Now J1 and J2 are distinct elements in P, and P already is a partition of this interval, so they are disjoint, and that is why it is this. Do you see the slight difference between the empty set and phi? To write phi, you write 0, which is lying down, and then strike it. Whereas to write the empty set, you write 0 and then strike it. This one is upright. And this, of course, is the empty set. So now we have all the pieces. Q is a partition of our interval, and already we have shown that if composition phi is constant on each element of Q, so it is piecewise constant with respect to this partition. WRT with respect to which if composition phi is PC is piecewise constant. But still we are not quite there, we still need one more thing. Next, we claim that phi inverse of J is equal to the length of J for each J in P. You should be careful to interpret this. This is not the phi image of the phi inverse image of J. No. To write that thing, we would write like this. There will be round brackets if we simply are talking about phi image of a set, but we have square brackets here, and this is the phi length of the interval phi inverse of J, just like we have alpha length. Without this identity, we won't be able to turn that Riemann-Stieltjes integral into Riemann integral. Okay, now we will prove this claim. So this is another part in the proof in the text where the author has left a question why. So now we need to answer this why. See, we already proved that for any such J, this phi inverse of J is an interval. So it will be of one of the 4 types of intervals that we know. Now, phi inverse of J is either a closed interval or a closed open interval or an open closed interval or an open interval whose endpoints are, say, alpha and beta, where alpha is less than or equal to beta. Okay. Now, no matter what phi inverse of j actually is, you note one thing, that all the sets in this set, in this collection of sets, are subsets of the closed interval alpha comma beta. So, phi inverse of j will be a subset of the closed interval as well. So, now if we take the phi image of phi inverse of j, this time we are really taking the phi image of phi inverse of j, not the phi length. On one hand, that will be equal to j. But the question is why? Why is it equal to j? In general, you do not have equality here. It is equal because phi is onto. I will see the I will write the justification. So this will be a subset of the phi image of alpha comma beta. Yeah. And the phi image of alpha comma beta itself will be phi alpha comma phi beta. Again, because phi is monotonically increasing and continuous, and the justifications are these. C corollary 974 and exercise 345. Corollary 974 justifies this equality and exercise 345 justifies this equality. Okay, so now we have this. So we know that j is contained in this interval. Okay. All right. But that alone won't really tell us anything about j. Okay, j is contained in this interval, but j can be anything in this interval. However, something else is also there. And that thing is this. Since alpha and beta both belong to phi inverse of j closure. Why? Say phi inverse of j is the closed interval alpha comma beta. Then its closure is also that interval because it is closed, so it is equal to its own closure and it has alpha and beta. If, however, phi inverse of j is this half open interval, then also its closure is the closed interval. So again alpha and beta are there. Similarly, if phi inverse of j is this or this, because the closures all equal this, alpha and beta are always in the closure of phi inverse of j. And because of this, phi of alpha and phi of beta both belong to the phi image of this closure. It is getting a little complicated, so let us be careful. Do we understand that? Yes, this is the phi image of the set which is the closure of the inverse image, phi inverse of j. However, this is a subset of phi inverse of j closure. Now this part needs the explanation. I will write the explanation, but let us first see what this becomes. Phi inverse of j is equal to j. So this becomes j closure. Now how is this a subset of this? Which means that we are using this result, that phi of some closure of some set S is a subset of phi of S closure. Should not close the bracket though. Is it justified? Do we already know this result? Well, we kind of know. Let us see. Its proof, in fact, is not very difficult. You take any element, see, what do you have to show? You just have to show that this is a subset of that closure. So you take an element here, say phi of z, where z belongs to S closure. Alright. Now because z belongs to S closure, there exists a sequence of points in S that converges to Z. You recall these results. Okay. We left these results behind long ago, but still they are there. So there exists a sequence Zn in S such that St, this sequence converges to Z. Limit of Zn is equal to Z, but our phi is continuous, right? So by sequential formulation of continuity, limit of phi of Zn will be equal to phi of Z, right? However, what can you say about phi of Zn? You see, because each Zn is an element in S, so phi of Zn is an element in phi of S for each n. That is why phi of Zn, this is a sequence in phi of S, and this sequence converges to phi of Z. So again, by one of the properties of closures, phi of Z being the limit of a sequence of points in phi of S belongs to the closure of phi of S, and that is why phi of Z belongs to phi of S closure. So that is how any element phi of Z which is here is also here, and that's why we were able to write this. In place of S here, here we have phi inverse of J. Okay. So what do we see now? One thing that we see is that J is a subset of this, but at the same time J should be a subset such that its closure has to contain phi of alpha and phi of beta, which are the endpoints of this interval, and that leaves us only with some choices for J. But then J will belong to this set of possibilities. Either it is phi alpha comma phi beta, in which case you can clearly see that they belong to the closure of this because the closure is this itself, or closed open interval or open closed interval or open interval. Okay, so J is either this or this or this or this, and no matter what J is, we can now write what the ordinary length of J is because we know its endpoints. So the ordinary length is phi of beta minus phi of alpha. However, this is nothing but the phi length of phi inverse of J. Why? Because the endpoints of phi inverse of J are alpha and beta. Yes, it's a different matter that it can be closed interval alpha beta or half open or open. And that's how we have this final claim proved. And now we can go back to that integral, which was the left side of our claim, final equation. The right hand side is this, and the left hand side is this Riemann-Stieltjes integral. So we know that this is the Riemann-Stieltjes integral of f composition phi with respect to phi and for the partition Q. So by definition, this is sum. Let me write J prime here. F composition phi. Let me temporarily write a notation like this. This means the constant value of this function on J prime times, because we are talking about Riemann-Stieltjes integral, the phi length of J prime. However, we know what the elements in Q are. They are phi inverse of J, where J is coming from P. So the sum changes to this. Phi inverse of J, which is actually J prime, and phi of phi inverse of J. And we know that this is Cj. And this is ordinary length of J. And now these two things are equal. So that is why this is equal to this. Do you at least see that we are kind of getting there? If this is your ordinary integral that you want to calculate and you make a substitution, then in place of the original variable x, you now have the variable phi. So you not only substitute phi in your integrand, but you also supply a d phi there. Okay, so it's going in that direction, where in place of dx we write cos theta d theta, or rather in place of cos theta d theta we write dx. So we will see where that ultimately leads us. But anyway, that will be all for tonight. And tomorrow also, as usual, we have our upload. And I think it's number theory, but I am not sure anymore. So we will see what it is. So see you tomorrow with the new upload. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.